In this video, we're going to cover section 9.3 on the acidity of acetylene, or ethyne, and terminal alkynes. Now, acetylene is significantly more acidic than ethylene, or ethene, and ethane. Now, the relative acidity of these hydrocarbons can be explained by exploring the stability of their conjugate bases. And the conjugate base of acetylene is referred to as the acetylide ion. As you can see in this figure, the pKa of ethene is 50, whereas the pKa of ethyne is 25. So that difference of 25 in a log scale is a 10 to the 25 difference in acidity. And so there's some significant stability associated with the acetylide ion relative to that of an alkanide ion. Now you may recall when we looked at the ARIO system that the orbital effect on the stability of a conjugate base can be significant when comparing the carbanions of various hydrocarbons. And so we look to the orbital in terms of the amount of S character present in that particular hybrid orbital. So an sp hybrid will have 50% S character, sp2 will have 33%, and an sp3 hybridized will have a 25% S character. And so given the greater amount of S character of the sp hybrid, the electron density is closer to the positively charged nucleus, and as a result is more stable. So if this conjugate base, the conjugate base of an alkyne, is more stable, then that implies that the alkyne is more acidic relative to the alkene or the alkane. You may recall that when we were discussing the equilibrium of an acid-base reaction, we said that it would favor the formation of a weaker acid and weaker base. So the pKa of the conjugate acid of a base must be greater than 25 for it to be able to deprotonate a terminal alkyne. And so you can see in this example, the base that we're using is sodium amide. And the amide ion, a strong base, can be used to deprotonate the alkyne. The result of this acid-base reaction is the formation of a molecule of ammonia and the alkanide ion. So the equilibrium favors the formation of the acetylide ion because it is a more stable, weaker base than the amide ion. Now, if we were to try and carry out the same reaction with sodium hydroxide as shown in the next reaction, we would see that if this reaction were to occur, we would form water and the alkanide. Now, because the acidity of water, the pKa specifically, is lower than the pKa of the original alkyne, this reaction will not favor the formation of what's shown here, products on the right side. The equilibrium will favor the formation of the weaker base and again the weaker acid. So in this particular example, using sodium hydroxide to deprotonate a terminal alkyne is not sufficiently strong enough to form the alkanide. So like ethyne, terminal alkynes are also acidic, and these can be deprotonated with a suitable base. And the net result of that reaction is the formation of the alkanide ion. So in your text, Table 9.2 lists a variety of bases and their conjugate acids. And as you recall, the strongest bases will be prepared from the weakest acids. And you can see midway through our table, we have the terminal alkyne, or the conjugate base of the terminal alkyne, and the pKa of the acid from which it came, in this example, ethyne, is around 25. And so in order to deprotonate ethyne, or terminal alkynes in general, we need to use bases that are stronger than the resulting alkanide ion. So we can use sodium hydride, sodium amide, or we can use carbanions as well. And so these bases are appropriate for the deprotonation of alkynes, terminal alkynes. As you can also see, the oxides are not sufficiently strong enough to deprotonate a terminal alkyne because the conjugate acid of these bases are stronger than the acidity of the alkyne. And so when we're carrying out deprotonation of alkynes, we're required to use a sufficiently strong base, and the most common one is sodium amide. So if you have any questions about the acidity of terminal alkynes, by all means, send me an email. Thank you.